Hey, okay, so I wanted to go over the 3 Google Forms we did last week. This is how you got your grade for last week, and if you haven't done them yet, you really need to because this is important, and it's also a good review for the test that'll be Friday. So there were 3 Google Forms that we did, one for each day last week. The first one was electric forces and electric fields. The second one was bees and pollen, distance and amount of charge, and the third one was Franklin's bells and detecting thunder. So you can find those in each day here, and you can also see that these titles of the days match the name of the forms pretty closely. All right, so first hour, or not really first hour, all you guys, electric forces and electric fields. So which of the following describes what an electric field is? An electric field is something that extends in all directions around an electrically charged object, right? Either it's coming inwards towards the object or it's coming outwards towards the object, but it goes all around it, omnidirectional. So this question, what do arrows represent in the models of the interactions of objects? So let me show you what that is talking about. So in this question, when it's talking about the arrows around a charged object, then what it's talking about is these green arrows, and that represents the electric field around the object. It represents how the charge is moving in comparison to that object. So we have positive charges going out, and we have negative charges coming in. Okay? So let's come back here. So question, electric fields surround all charged objects. Is that true or false? It is true. Yeah, a charged object has an electric field that either radiates out from it or draws into it. And question, a single charged object will experience either attraction or repulsion. So let me show you how we answer that one. A single charged object, reset. So here we have 2, hold on a second. So we were looking at 2 charged objects around each other, and we know that that's kind of what that looks like. But if we only have 1, then what was the question here? A single charged object will experience either attraction or repulsion. Okay, so when we have 2 particles, we have these forces of attraction and repulsion, right? But when we only have 1 particle, there are no forces going on here, right? This is like the grandma sitting at home. She's thinking about all her grandkids and how she wants to give them cookies, but nothing is happening right now. There's no forces going on. Same thing if this was negative. This is the Cookie Monster dreaming of cookies, wishing for them, but there's nothing going on here. He's just sitting there dreaming of it, okay? So there's no forces on a single object. There's only forces when they come into contact with each other. So then we have this figure right here, the electric field between 2 positively charged objects. So what force would the 2 positively charged objects in figure 3 experience in figure 3 above? So we have 2 positive objects, so you guys know what that's going to cause. That's going to cause repulsion, right? What evidence do you have from the simulation screenshot to support your claim in the previous question? So that means, what do we see in this oval here that's showing that repulsion? So what we're seeing is these 2 fields interacting here. They are pushing against each other. Let me show you another example of that. So when we have these 2 positively like charged objects, right? They are acting like these 2 grandmas right here that need their own space, right? So they have these 2 electrical fields that are pushing up against each other. They're never touching and they're not overlapping. They're pushing against each other and wishing they had their own space. That's what's going on there. And same thing if we had 2 negative charges. That's like 2 Cookie Monsters hoarding the cookies. They need their own space. They need their own cookies. They're going to push against each other because they know that they need their own space, right? Okay, so what we see here is that we have those lines pushing upward and downward. They're not pointing at each other in the middle so much. Okay, what do you think the simulation would show if you were to place 2 negative charges next to each other? Be sure to talk about the direction of the green arrows around each charge as well as in between the 2 charges. So 2 negative charges are going to look like this, right? So we have all the charges are pointing, or all the electric field lines are pointing in towards those negative charges, but when there's 2 of them close to each other, there's going to be that like curve between them, and it's going to send particles you know, like if we placed a negatively charged particle in between the two, it's going to shoot it up or down, okay? Let's come back here. What do we think the simulation would show if you were to place a negative and a positive charge next to each other? Be sure to talk about the direction of the green arrows around each charge as well as in between the two charges. So that's going to look like this, okay? We're going to have the positive reaching out and the negative taking it in, and it's going to be this big circle, right? Because the positive loves giving and the negative loves taking it in, okay? They love each other. Okay. How can objects interact with each other without actually touching each other? You guys have a lot of answers for this now, and I'm going to let you come up with those words to answer that on your own. But make sure that when you answer it, you're using the words charge, you're using the words electrical fields, and you're using talking about forces, electrical forces as well, okay? Okay, so here's Wednesday's Google form. First hour, bees and pollen, not first hour, sorry, I'm just reading. Bees and pollen, distance and amount of charge. The electric field surrounding a negatively charged object, the Cookie Monster, right, points inwards. Those charges are coming in towards it. The electric field surrounding a positively charged object points outward. The grandma wanting to give the cookies and give the magazines and give the love and all that stuff. So where is the electric field strongest surrounding a Van de Graaff generator? Remember, we had, well, we can think about the tape demonstration, but it's going to be closest to it. The charge has, the electric field is strongest closest to the charged object, okay? But it's all the way around. It's not like it's more strong in one spot. It's definitely, it is a spherical force field that is drawing equally from all sides, as long as it's just its own one charge, okay? What do different lengths of arrows, we're talking about the yellow arrows here, what do they mean on our models for activity 2? So short arrows mean that there's not a lot of force between them. That'd be like, let me show you this. So here's some short arrows because they're weak charges. They, you know, they don't really like each other, but they don't, you know, there's not a whole lot of force to want to move. And the farther away they get from each other, the shorter those arrows get. Whereas if we have very strongly charged particles, then in that same distance, those arrows get really long, meaning that those two very strongly charged negative particles are going to want to just shoot apart. They have a lot of force pushing them apart from each other. Okay, so let's come back here. What pattern do you notice about the strength of the electric force between two charged objects as the distance between them changes? So the electric force gets stronger the closer the charges are, okay? When the charge on one object is increased, either positive or negative, what happens to the forces on both objects? So let's come over here and look at that. What if we have one very charged object and one not so charged object? I notice that right now those arrows are the same length, and I notice that I bring it closer, they're still the same length. When I bring them farther away, they're still the same length. So those forces are acting equally on both of them, even though one has a much stronger field than the other one. The net balance between them is an equal force between them. So then we have these simulation questions. We have point A, point B, and point C next to a negative charge. So at what point is the electric field around the negative charge the weakest? So that's going to be the point that's farthest away because the electric force is strongest closest to the charged object. So if you could create a positively charged object at any of these points, where would you place it to create the strongest force between the two charges? A positively charged object is going to repel this one, right? So where would you place it to create the strongest force between the two charges? I know that the electric field around this charged object is strongest closest to it. So if I would like to place something that's going to react very strongly to that, I'm going to place it close. So I'm going to pick B. Okay, so then you have that reading, how do bees find flowers? Here's a bee pollinating a flower. So the ways that bees pollinate flowers, they can smell them. They can also see both visible and ultraviolet lights given off the flowers. And they can also detect the electric fields of flowers. So a bee, as it's flying through the air, gains a positive charge because of that fur. It's triboelectric. When that fur is rubbed, it wants to give up electrons, meaning it gains a positive charge. So it comes to that flower, and that flower has been producing pollen, and that pollen has a negative charge. And so it's drawn in there, and then when it sits on that flower, the pollen goes and is just like stuck onto the fur of that bee. So how does a bee identify a flower with pollen versus a flower without pollen? So a bee is sensing those electromagnetic fields. Isn't that cool? Like that they, just like they can see frequencies of light that we can't see, they can also detect electromagnetic fields that we can't detect either, at least not consciously, right? Describe how you would draw a model of a flower before being visited by a bee. Make sure to include the direction and the length of the arrows in your description. Okay, so a flower that has negatively charged pollen on it is going to have a negative electric field. And I know that just like the Cookie Monster, the negatively charged electric field points inward. So if it has a lot of pollen, a lot of negatively charged pollen, it's going to have a long inwardly pointing arrows showing that negative electric field. So describe how you would draw a model of a flower after being visited by a bee. Make sure to include the direction and the length of the arrows in your description. Okay, so once that bee has come and that pollen has sucked onto it, then that bee has taken that negatively charged pollen away. So now that flower is going to have more of a neutral charge. It may still have some pollen on it, so it might have a slight negative charge, in which case it would have short, inwardly pointing arrows. That's, I think, probably the safest thing to say there. I know when I showed you the demonstration of it earlier, I had it totally neutral, but chances are it's still got some pollen on there, so it would have a weaker negative electric field on it. Okay, I only have 3 more minutes to make this video before it cuts me off, so let me get through this next one real quick. Okay, so Franklin's bells. Okay, so once the Van de Graaff is turned on, what causes the ball to swing towards can 1? So this Van de Graaff is over here creating this positive charge, which is transferring over into this can. So this can now has a positive charge. So this neutral ball is going to swing towards that charged can because that charged can wants the charge, the negative charges that are in that neutral ball, right? So it's going to come over there. Okay, so that's the answer to that one is in there. When the ball hits can 1, some of the electric charges are transferred to the ball, right? Positively charged thing, and it takes it, and then that ball has a positive charge also. So we have this positively charged can, positively charged ball, and now they're like, ugh, 2 grandmas, I need my own space. So it comes over here to can number 2, and that is because of repulsion, right? Because that positive and positive comes over here, and then it transfers that positive charge to can number 2, right? So swing towards can number 2. Why is the ball attracted to can 2 and after leaving can number 1? Because can number 2 is neutral, right? So now we have this charged ball, and it's hitting this neutral can to transfer that charge over. Okay, so why did Franklin's bells stop, right? We had that moment where she turned off the Van de Graaff machine, it kind of rang for a second, and then it came to a stop. But then when she put her hand near it again, it started to ring again. So if Franklin's bells were left to run for a while, what would the charges be on can 1, the ball, and can 2? Eventually, that charge would all even out. There would just be like a huge positive electric field around all the way around the Van de Graaff machine, including the cans and the ball and the other can, because that ball keeps transferring that charge over. So they would all have the same charge as the Van de Graaff. How we know when all 3 objects have the same charge is they're going to stop moving. That movement is only to balance out the charges, but if they all have the same charge, then they're just all kind of like basking in that same charge. Think of it like the charge is flowing through them all evenly. In order to get the bells ringing again, all we'd have to do is touch can 2 to a piece of metal, or like when that woman reaches her neutral hand out, right? Then it draws the charge away. She's grounding it. Same thing if we put a piece of metal on it, it would ground it. Okay, I've got like 10 seconds left. How am I going to do this? 8 seconds. Positively charged upper part of the cloud, negatively charged under part of the cloud, which brings the positive charges in the Earth